Okay, so we're going to have a look at the answers to the recent test, the first AS Chemistry mock we did after Easter. Right, so the question was, we had to explain the difference in size between a sodium ion and a fluoride ion. It told us up here that they have the same electron configuration. Okay, so both of them have an electron configuration of 2,8. Okay, so the question is, why was the sodium ion, or sorry, why is the fluoride ion larger? Well, that's because the fluoride ion has got 9 protons in the nucleus. Sodium ions have 11 protons in the nucleus. So if you have 11 positives attracting 2,8 electrons, it pulls them into a smaller volume of space. Over here I only have 9 positives put in on the same 2,8 configuration of electrons, so that ends up being a larger ion, sorry, not a larger atom. Right, second one we had to explain in terms of structure and bonding, so you must refer to those, why the melting point of sodium fluoride is high. Okay, so sodium fluoride, first thing about structure and bonding is that bonding is ionic, okay, and the structure is a giant lattice, okay. And what is it about that means that it has a high melting point? Well, you have got very strong, okay, and I'm just going to write shorthand here, ES, electrostatic attractions. Okay, I'm writing out the perfect answer here really, and those electrostatic attractions are between, and you would there refer to oppositely charged ions. Okay, this is actually a GCSE question, guys. Okay, and the last thing is you would say, I make some reference to the fact that you need lots of, and I would prefer you talked about heat energy rather than energy, okay, to break those bonds that we've just spoken about. Okay, right, the next one then we had HF reacting with an H plus ion, and what type of bond was there between the HF and this H plus ion? Right, H plus has no electrons. It has now formed a covalent bond in here, okay, but it had none of its own electrons, so it must have used a lone pair of electrons. The only place there is lone pairs on here is in the fluoride. Okay, so the type of bond is the date of bond, or the coordinate bond. Okay, why is it a coordinate bond? Well, because it has used a lone pair of electrons specifically from the fluorine, okay, to form that bond. Right, shapes of these things, well, that is SB, F6, so it's SB in the middle. F6 must be, okay, you need to be able to draw these three-dimensionally, guys, so please make sure you practice. Okay, you'll have your F's at the end of each of those. That is octahedral. Okay, and our HF2, okay, if you look at our, if you look at our HF2, you will see that my F is there, my H is there, my H is there, and on this fluorine we end up having 2 lone pairs of electrons. Okay, if you draw out the dot cross diagram, and therefore it is bent. I had a few people talking about this being linear, but linear would not apply whenever you have the 2 lone pairs of electrons there, guys. Okay, this one then caused a little bit of difficulty in that what we had to do was sort of the reverse here. We got the delta H and we had to go back and work out the energy needed to break the H, to break one of the HFs. We weren't doing both of them, we were just doing one. So you had to add up all of the energy needed to first of all break the bonds. Okay, so in here we had our 8, I'm talking about the left hand side of there, we had our 836, we had 2 of the 837, sorry, 2 of the CHs, and then over here we had 1, 2, 3, 4 CHs, 1 carbon-carbon bond, and 2 carbon to fluorine bonds. Okay, so because we got our delta H this time, that meant that minus 179 was equal to, okay, the 2785 minus, okay, so that's the energy needed given out there, by the way, okay, minus the 1996, okay, plus the 2 CF bonds. Okay, sorry, that's the energy taken in to break all the bonds on this side. Sorry, we're calculating the CF bonds, apologies, not the HF bonds. Alright, so if you did that, you would have, if you rearranged that, you would have found that 968, a lot of us forgot about this, okay? 968 is the answer to that, is equal to the 2 CF bonds, and you simply divided therefore that by 2, and that would give you the strength of 1 CF bond, which came out of that. That should be a positive value, by the way. Okay, you didn't have to put a unit on it, but if you put negative on it, you would have lost marks for sure. Right, complete the electron configuration of the chromium. Right, so remember in transition metals there are two configurations that are dodgy. Okay, chromium is one and copper is the other one. Okay, you also have cobalt in there starting with a C. It's not cobalt. The way I used to remember to school was no. Okay, so not cobalt. Alright, so the electron configuration of that is 1s2, and then we go to 2s2, and then we go to 2p6, sorry, I forgot my s, 2p6, 3s2, and then we go to our 3p6, everything's all fine until then. Then we get to our 3d and our 4s, right, these are now half fill, that's why it's funny. Normally you would expect 4s2, 3d4 if it followed the trend, but that doesn't give you two half fill subshells. That's what we were after there. Okay, deduce the symbol including mass number and atomic number of this atom. So we've got an atom that has 2 more protons, okay, and 3 more neutrons than chromium. Okay, so if it has 2 more, so if you go to your periodic table, okay, it would have been what I would have done, and I would have found chromium, which is of course 24. Yes. Okay, so the number of neutrons in that is 24, 28, so we've got 28 neutrons in that. Okay, this thing has 2 more protons, so if there's 24 protons in that, okay, we must be going up to 26. Okay, so 26 is the atomic number, and if we go to our periodic table and we find 26, okay, therefore that tells us that it is iron. Alright, we thought that this had 28 protons, okay, 28 neutrons. This one has 31 because it's got 3 more than that, so we have 26 plus the 31 gives us 57. 57 is therefore the top line, or the mass number I should say. There's no charge on it, okay, there's no reason for a charge. Okay, some of you had written a negative charge on it. I couldn't quite work out why that was. But anyway, hopefully you can see now why it is as it is. Right, determine the percentage abundance of the 4th isotope. Okay, so well, the 4th isotope, I mean, we've got percentage abundance of 1, 2, and 3. We just add them together and take it away from 100. That was 3.6. Believe it or not, you actually got 1 mark for working that out. Fairly unbelievable. Yes, I would get that. Then we had to show by the calculating this mass is actually 50. Right, so it tells us up here that the atomic mass is 52.09, yeah? So 52.09 will equal, I'm not going to write all this out, it will equal the 52 multiplied by the 82.8 plus the 53 multiplied by 10.9 plus the 54 multiplied by 2.7, okay? Show that the calculation of this isotope is 50. Well, therefore we also add to that 50 multiplied by 3.6. Okay, so that plus that plus that plus that, and all of that you had to show is equal to 52.09. And if you did that calculation, therefore you got your other 2 marks. Right, deduce the oxidation state of chromium in here. Most of you probably know it anyway. So you have 2 chromiums, we'll call them 2 X's, plus 7 oxygens, so that's, each oxygen is -2, so that's -14 equals 2 minus, okay, so 2x minus 14 equals 2 minus 2 I should write there. So x, the 2 x's must equal 12, 12 minus 14 is -2, so each one is 6 plus 6 oxidation state. Okay, right, the next one then, you had to deduce the half equation for the oxidation of iodide to iodine. Right, well, you should know iodine is as so. Iodide ions are -1. I'm going to need 2 of them. Okay, I got to balance up my electrons on the half equation. I need 2 electrons on that side. We then had to go dichromate, I should say, to chromium 3 plus. So when we're doing our half equations in redox, first thing we do is balance everything except oxygen and hydrogen, chromium that is, I need 2 of them. Then we balance oxygens with water molecules. I have 7 oxygens on the left, I need 7 water molecules. Then we balance hydrogen atoms with hydrogen ions. I have 14 hydrogen atoms on the right, I'm going to need 14 hydrogen ions on the left. Then we balance charges. On the left hand side I have 2 negative here and 14 plus here, so I have 12 positive on that side. Here I have 2 3 positives, so I have plus 6. I'm going to need 6 E minus on that side to balance that up. The next part of this question then was that we had to combine the 2 half equations here and here, okay? So in order to do that, what you need to do is take the number of electrons and reduce them to the lowest common multiples. So we have 6 and 2, so that goes to 1 electron, and this one then goes to 3 electrons, and we take that electrons and multiply everything in that equation by 3. These electrons here multiply everything in that equation by 1. So your final answer, I'll just write it up here, okay, should have been a Cr2O7 2 minus, plus we have got 6I minus 3 times the 2I minus, plus we have our 14H plus, that's just multiplied by 1, okay, and that goes to, we have 2Cr3 plus, plus we have a 3I minus, ignore that, 3I2 plus 7H2O, and that is your final answer. Right, this one we have the equilibrium expression, and you've got our equilibrium reaction, you've got to write the expression. The expression is square brackets, okay, the concentration of the products risen to the stoichiometric number, which is 2, over the concentration of the reactants, okay, which is again risen to the stoichiometric number, and multiplied by, you don't have to write that sign in, you can just write them beside each other, Cl, you have to write Cl2, had a few people just wrote Cl, which cost them the mark, hopefully you won't do that again, and that's your answer, that's the Kc expression. Right, this one then we had to use the results to work out the MR of HA, right, so we had the first thing we had to do was work out, of course, the mean titer. Right, we don't use the rough, and the other thing that a lot of us didn't pick up on was that we had an outlier here, and we don't use that one either. That would have cost you 1 mark if you used that in your average. These are the 2 accurates, these are the 2 concordants. Okay, so the mean you should have worked out at 26.45 cubic centimeters. Okay, right, so if we read the question, in the question, if you go through it, okay, we'll just draw our conical flask on our Buret here to see what's in where. So 250 cc's of an aqueous solution of HA was made, so we'll just write that up here, 250 cc's, and it used 1.3 grams of HA, 1,300 milligrams is 1.3 grams. A pipette was used to add 25 cc's of 0.1 molar sodium hydroxide to a conical flask. So we put our this into the conical flask, and we put 25 cc's into it of 0.112 molarity, and that's my sodium hydroxide in there. So in other words, my acid is in there. So in other words, my average titer here refers to my acid. I think a few of you got this back to front, which cost you dearly. Alright, then what we had to do was we had to work out the MR of the acid. So remember, MR is equal to mole mass, I should say, over mole. So I've got to get mass, and I've got to get moles. Well, mass I've been given here already, so we'll come back to that. Okay, so if we look at the equation here, you can use this to work out the number of moles of my sodium hydroxide. We just do a number of moles equals concentration times volume, and that is, as you would all know, over 1,000. Okay, so my moles of sodium hydroxide works out at 2.8 times 10 to the minus 3. Okay, so my moles of acid, which is, remember, over, if we look back to the equation, it's a 2 back to 1 ratio, so that's 1.4 times 10 to the minus 3. And remember, that's in my volume that was used in the titer, so it's 26.45 cubic centimeters. Now that came out of 250 cubic centimeters. So if I multiply that by 250 over 26.4, I'm basically scaling this up to how many moles I had in 250 cubic centimeters. That comes out at 0.0132 moles, and that's in the 250 cc's, right? Okay, now that number of moles was equivalent to 1300 milligrams, or 1.3 grams. So 1.3 grams divided by 0.0132, so we're simply using our MR equals mass divided by moles, and that gave me 98.2 grams was the MR of the acid. And that was your answer. Okay, every mistake you made, you lost a mark. So there's a variety of ways of still picking up four out of the 5 marks here. Right, percentage uncertainty in a Buret. So percentage uncertainty is measured by the uncertainty divided by the volume delivered. The pipette, in the pipette you delivered 25.0 cubic centimeters, and that's times 100, and you got a percentage uncertainty of 0.24. Some of you had this multiplied by 2, which is the percentage uncertainty what you would use for a Buret, because in a Buret you have 2 readings, the initial reading and the final reading. That's not appropriate when you do this with a pipette. There's only 1 reading. It's only worth 1 mark, so if you did make that mistake, unfortunately you lost all marks. So explain why an air bubble increases the final Buret reading. Well, okay, if you have an air bubble, you have to add the air plus some solution. Okay, and if you think about your Buret, guys, if I draw sort of an air bubble there, yeah, and your Buret, when the air goes out of it, the Buret reading will still go down. Okay, but the air bubble doesn't actually neutralize anything in the conical flask, so you're going to have to add air, which does nothing, but is going to give you a reading on your volume, so your end reading is going to be bigger than you might anticipate. Right, suggest why washing the flask does not give an incorrect result. If I sort of go back to here, if I wash the flask here, what am I using the flask to actually do? Well, if you look at it, we're just using the flask to work out number of moles. That's it. The calculation that follows allows us to get concentration. Okay? So if I wash this down with deionized water, it doesn't affect the number of moles. Okay? The other thing about the deionized water, it doesn't react with anything. Okay? So that was your answer. First of all, it has no impact on the number of moles. Okay? So the number of moles is unaffected. Okay, and I'll not write it out, but the deionized water doesn't react with anything in the flask. Some of you said adding the water doesn't affect the concentration in the conical flask. Well, it does affect the concentration, of course. Adding water will do that, but it doesn't affect the moles. I couldn't give you a mark for saying it doesn't affect the concentration. Okay, next one then, we had to write an equation. We were talking about magnesium is used to extract titanium. Give the equation of titanium 4 oxide with magnesium. So you had to work this one out. So magnesium, of course, titanium 4 chloride, chloride is oxidation state 4, chlorine you know is 1, so it's that. And then you had to balance this out, and I went to magnesium chloride. Okay, so I'm going to need 2 of those because I have 4 chlorides on the left, plus titanium, of course. Now, what's the role of the magnesium? Titanium starts +4 oxidation state, and titanium ends up at 0 oxidation state. So it's been reduced. The only thing that it could have been reduced by is the magnesium. So the magnesium must be a reducing agent. The reason why I say the only thing can be reduced by is because the chloride starts at -1 and the chloride finishes at -1. So it's unaffected by the redox that's going on in there. Right, here we had to calculate the percent. This was a difficult question, but fairly reflective of a AS chemistry difficult question, guys. Right, let's have a look. So a mixture of magnesium oxide, and hydroxide had a total mass, so both of those things together had a total mass of 3.2 grams. I'm just changing it from milligrams into grams. Okay, when they reacted, they made 210 milligrams of water. That's 0.21 grams of water. Okay, the reason why I'm turning grams is because my moles equals mass over mR. That is in grams. Okay, now the only place the water can come from is the magnesium hydroxide, not from the magnesium oxide. So if I have that number of mass, of water, and I divide that by 18, that will give me the number of moles of water that I had in here. Okay, and if I get the moles of water, which comes out at 0.0117, so 0.0117, that is equivalent to the moles of magnesium hydroxide, because they're in a one. If you look at the equation, water to magnesium hydroxide is a 1-to-1 ratio. Okay, now if I've got the moles of magnesium hydroxide, I multiply it by the RFM of magnesium hydroxide, which is 58. That tells me that in here I have got 0.68 grams of magnesium hydroxide. So out of the 3.2 grams, 0.68 grams of it, okay, is the magnesium hydroxide. So the rest of it, the 2.52 grams, must be the magnesium oxide. So I just do a simple percentage then. So the 2.52 over the 3.2 times 100 tells me that I've got about 78.7% of that substance is magnesium hydroxide. Okay, this time we had to work out how we were going to differentiate between these particles. So in here, we can't use the chloride ion because it's the same in both. So we've got a barium ion or a sodium ion. We have to use reagents. We can't use flame tests, therefore. Okay. So let's see how, and we were only allowed to use a single reaction. Right. So how do I test? Well, I would use something with sulfate ions in it. Okay. SO4 2-. Now, some of you did write here sulfate ions, but it asked for a reagent. You can't have a reagent of sulfate ions, okay? You have to have something with sulfate ions in them. So sulfuric acid, for example, you could have used potassium, another solution of sulfate ions, yes? Now sulfate ions will combine with barium ions, so they do nothing, okay? There is no visible change here, okay? And here you get a white precipitate. That's barium sulfate. So sulfate ions react with barium ions to give you that. Here you could have used silver nitrate. You had to say, however, it was silver nitrate solution. You could not say silver nitrate, because silver nitrate is a white solid, and your observation that you're going to get here is also a white solid. Okay, so you can't actually use a white solid to get a white solid, if that makes some sense. Okay, so you could use indeed silver nitrate, and that should also be acidified silver nitrate with dilute nitric acid. Okay, so with the chloride ions you will get a white PPT, and with the sodium carbonate you will get no PPT, but because of the acidified you will get fizzing. Okay, bubbles, colourless gas, effervescence, something like that. Right, multiple choice section then. Next. So which sample measured at room temperature and pressure contains the greatest number of stated particles? Right, so we had to do here, we had to get into Avogadro's number. Okay, so the first thing we need to do is get moles. So moles equals mass divided by the RFM. Okay, and then particles equals moles times Avogadro's constant. Remember, that's 6.02 times 10 to the 23. It's on the back of your little periodic table. Okay, so we had 1 gram of hydrogen molecules, so that's 1 divided by hydrogen molecules is H2, so there's a mass of 2 times Avogadro's number. 1 gram of helium atoms, that's 1 divided by 4, so that's a quarter multiplied by Avogadro's number. Now, this is going to be less than that. So a half divided by Avogadro is less than a quarter. So I would get rid of that. 1 decimeter cubed of hydrogen molecules. This was rather sneaky. This is now using the gas molar volume. Okay, so 1 decimeter cubed is 1 over 24 moles multiplied by Avogadros. Okay, remember moles of a gas is equal to volume divided by the molar gas volume, which is 24. Okay, well, the volume in decimeters cubed, I should say. So that's 1 over 24 multiplied by Avogadro's number, which is just simply not going to be anywhere near what we have up above. 1 decimeter cubed of helium atoms, that's exactly the same as that. That's still 1 over 24 times Avogadro's number. The answer is A. Right, next one, 5 grams of an oxide of molybdenum contains that amount of molybdenum. What's the empirical formula? Right, okay. So, first thing that we had to do here was go to our periodic table and find molybdenum, which is 90, has an atomic mass of 96. Okay, so the amount of that in there is 4 divided by 96. Okay, and the amount of oxygen in there is 1, so the 5 minus the 1 divided by 16. Okay, so if I punch those numbers in, so we've got 4 divided by 96 gives me, that's 1 over 24, and we have 1 divided by 16 gives me 1 over 16. Okay, the ratio of 1 over, so divide that by 1 divided by 16 equals 1 divided by 1 divided by 24 gives me a 2 to 3 ratio. A 2 to 3 ratio. Okay, so the answer therefore, the only one that fits that is C. Okay. Right, which substances delocalize electrons? Well, it's graphite, simple as that. It's GCSE answers, what is anything? Which species is not pyramidal? Okay, so if we look at all of them, pyramidal would be you have something with 1 lone pair and 3 bonded pairs. So if you go through that, and that, you will find that that's exactly what they have. BF3 you should probably recognise as something with a reduced octet. Boron only has 3 outer shell electrons and it's bonded to 3 fluorines, so it only has 3 bonded pairs, so it cannot be pyramidal. It's going to be trigonal planar, by the way, if you're interested. Which change occurs when water vapor is vaporized? An exothermic change occurs. Okay, an exothermic change does not occur. That's endothermic. You're vaporizing water, you're putting energy in. Covalent bonds are broken, absolutely not, because if you're vaporizing water, you're just turning it into water gas. If you broke the bonds, you'd have hydrogen and oxygen. Intermolecular forces are overcome, of course they are. That's exactly what happens. Okay, the total energy of the molecule decreases. Well, no, if you turn something into a gas, you're going to increase the energy of the molecules. Right, next one. Which one of these represents the standard enthalpy change for formation? So enthalpy of formation is defined as the energy needed to form 1 mole of a substance from its elements in their standard states. So let's go and find the elements in their standard states. Well, barium's a metal, so that's gone. These are not the elements. This is a barium 2 plus ion, so that's not an element, and it's not in a standard state. Down here we have it in a standard state, but it's an ion, so that's not going to work either. Same for the chloride ions. Here, C, standard state, 1 mole of the solid. That's your answer. Which one of the following does not represent redox? So we're looking for changes in oxidation numbers perhaps here. Okay, so if I look at this one, magnesium is 0, here it's +2. Okay, hydrogen here is +1 and hydrogen here is 0, so there's redox going on there. Okay, if I look here at my iron, that iron is 0, this iron here is now +2, this copper here is +2, this copper here is 0. That is not the answer either. Okay, redox, we have here the carbon in this particular one is gaining oxygen, okay, and the hydrogen here and it is losing hydrogen, so gaining oxygen, losing hydrogen, so that is redox, different definition than the other two, but nonetheless, this one here, copper is +2, oxygen is -2, hydrogen is +1, chloride is -1, copper is +2, chloride is -1, hydrogen here is +1, oxygen is -2, there is no redox change there, so that answer is D. Which property would you expect radium to have? Well, if we look at radium, you'll see it's right at the very bottom of group 2, okay? So we would expect it to form a soluble sulfate, no chance. Barium sulfates become less soluble down the group. It does not react with water. It certainly would react with water. Is a good conductor of electricity? Yep, of course it would be. And the last one is the fluoride is ionic. Is covalent? Definitely not. Down there, that's a very electropositive metal, and the fluoride is very electronegative, so it's going to be very ionic. Right, which statement is not correct for number 17? Strontium has a lower first ionization energy than calcium. That is definitely true. As you go down the group, the first ionization energy decreases, so that's your trend. Strontium has a larger ionic radius than calcium. Of course it does. It's below calcium in the periodic table as an extra shell of electrons. Strontium reacts less vigorously with water than calcium. Yeah, that is rubbish. That is not correct. As you go down the group, reactivity increases. Okay, strontium hydroxide is more soluble in water than calcium hydroxide. That's true. As you go down the group, the sulfates become less soluble, but the hydroxides become more soluble. Which property of the group 2 elements increases with atomic number? Okay, so well, atomic radius, simple as that. Okay, the bigger the atomic number, as you go down the group, yeah, you're going to add an extra shell each time, so it's atomic radius. Which is the best this is a question about group 7 chemistry this time. The best oxidizing agent is the one that is most easily reduced, so this thing has to be able to gain electrons, so that rules that out, and it rules that out because for those to gain electrons I'd have to go to F2 negative and I2 negative. That's just doesn't exist. Okay, oxidizing agents get reduced, so that means which one of this or this is the best at gaining electrons? Well, the fluoride is the best at gaining electrons because its nucleus is closest to its outer shell, so if there's electrons around, the electrons are far more attracted to the fluorine than they are to the big old iodine. So fluorine is good at getting electrons, in other words getting reduced, so it's a good oxidizing agent. Okay, question 20. Right, so some fuel and spirit burner, okay, was used to heat a container in the experiment. Okay, the mass of the water was that. Okay, what is the amount of heat energy absorbed by the water? Okay, so the heat energy absorbed is Q equals mc delta T. Okay, so what they've done here is the M is the mass of the water absorbing the heat. There's M. The Y they've represented as that, and the C they've represented as the heat capacity. So it's just MCY. Okay, it's just that. Alright, so instead of MC delta T, they've just changed delta T, if you like, temperature rise to Y. Alright, so nothing more than that. Question 21, we're nearly there. Okay, so the equation below represents a complete combustion of butane. 20 cc's of butane, okay, are completely burned in 0.2 decimeters cubed. Okay, so I just turned that to cubic centimeters, so we're kind of working in the same units. Which statement is correct? All volumes are measured at the same temperature and pressure, right? 40 cc's of carbon dioxide are formed. Well, let's just work out what's going on here. We've got 20 cc's of that. Okay, that will require 150 cc's of 6.5 times 20 cc's of oxygen. So you're going to have 70 cc's of oxygen left over in here unreacted. Okay, which also means that the oxygen is in excess. So my limiting reactant is this, yes. And if my limiting reactant is that, and I have 20 cc's of that, it's a 1:4 ratio to carbon dioxide. So I'm going to make 80 cc's of carbon dioxide, and I'm going to make 1:5. I'm going to make 100 cc's of that. So let's see if any of these are right. So which one of the following are correct? 40 cc's of carbon dioxide will be made. Nope, already worked out that won't happen. 0.065 decimeters cubed of oxygen reacts. No, because it's 20 cc's, so it'll be double that, my 130. 70 cc's of oxygen remains. Yeah, we've worked that out up there. We had 130, we've 70 left over. That's the answer. And 50.5 of a decimeter cubed of steam, 500 cc's of steam is made. No, there's only 100 cc's of steam made. Which of the statement is correct involving halide ions? This is group 7 chemistry, okay. Again, group 7 halogens. Sodium chloride forms from chlorine when added to concentrated sulfuric acid. Sodium chloride reacts with chlorines added to conc sulfuric acid. Well, no, that's not going to be true. Okay, where does the sodium come from is really what you should ask yourself there. Okay, sodium chloride forms when chlorine sodium chloride forms chlorine, sorry. No, I've read that wrong. Let's go back to the first one. Sodium chloride forms chlorine when added to conc sulfuric acid. No, it doesn't. Okay, when chloride ions are added to conc sulfuric acid, you get hydrogen chloride, okay, and you get